Alright, here's my video guide for lesson 10.1.3. The idea today is we're going to look at the relationships with polygons inscribed in a circle and the lengths of intersecting chords. That's really just going to be using what we've done the last 2 days to kind of investigate something new. And what we did the last few days really was talking about inscribed angles and central angles, and on Tuesday we talked about a perpendicular bisector to a chord. A lot of that's going to come back, especially that idea of the inscribed angle being half of the central angle. That one comes back quite a bit here today. We'll start here at 10-25, and it's actually kind of similar to the homework problem we did yesterday. So it says, what is the measure of an angle when it's inscribed in a semicircle, an arc measure with 180 degrees? Consider this as you answer this next question. So assume that the diagram at the right is not drawn to scale. If the measure of QR, so that arc length right here, or that arc measure of QR is 180 degrees, then what is the measure of P? Well, this is, like I said, what we did yesterday for homework, is we would say that if that arc measure length there is, and I'm going to try to get this right with my lines here, if that arc measure length is 180 degrees, that means the central angle is 180 degrees, because the central angle is always the same thing as the arc measure on the outside. And then, like I said in the beginning of the video, that inscribed angle is always half of your central angle. And so the measurement of angle P must be 90 degrees. And so that's going to be my answer for part A here. And that is, like I said, what we did yesterday in the homework, and just that idea that if we know the measurement of an arc, we know that that could be the measurement of the central angle of that arc, and then the inscribed angle is always half of that. And those are all related, because if you look at that central angle right here, it goes out to Q, goes out to R, and that's 180. And then if you look at that inscribed angle P, it goes out to Q and it goes out to R. So I know that they all are talking about that same arc measure QR being 180. And so we'll say that A is 90 degrees, and that's where we're going to move on from. All right, explaining why, I kind of did that just verbally here, saying that I took that 180, knew that that was the central angle for QR, and then angle, or the inscribed angle P, is always half of that central angle. All right, since you have several tools to use with right triangles, we have quite a bit. The special relationship you found in part A can be useful. For example, UV is the diameter of the circle. So UV is the diameter, it's cutting it perfectly in half. TU is 6 and TV is 8. And now it's looking for the length of the radius and what is the area. So really what we're going to look for first is what is the length of UV, because that's the diameter. Then we're going to cut the diameter in half to find the radius, and then we're going to use that radius to find area. All right, one thing I don't really love about this problem is that they talk about how we have tools for right triangles, but they don't really say this is a right triangle, but we do need to assume it is. Otherwise the problem won't work. All right, and so that means TU is 6, TV is 8, and UV we're missing, so I'm going to call it C. If it's a right triangle and we know two of the sides, we can find the third side by using the Pythagorean Theorem. And so you get A squared plus B squared equals C squared. A and B are the legs, and C is the hypotenuse. And in our case, that's the right way it's written, because C is across from the 90. So C must be the hypotenuse here, and that's the only one we don't know. So we're going to replace the other ones, and it doesn't matter how you replace them. So we'll do 6 squared plus 8 squared equals C squared. Again, C is representing that diameter UV. 6 squared is 36, because that's 6 times 6. 8 squared is 64, because that's 8 times 8. C squared is still C squared. Add them together, 36 plus 64 is 100. And then so that to get this so it's not C squared and it's just C, we square root both sides. And what we get for an answer is that diameter is equal to 10. So instead of this being C, that's equal to 10, which means that the radius is that cut in half. The radius is equal to 5 because radius is diameter cut in half. All right, so now we have our radius, and we just need to find area. So we have to do area of a circle is always pi times the radius squared. And so our area is equal to pi times 5 squared, because that's our radius. And so the area is equal to 25 pi. If you put it in a decimal form, that's all right. I always kind of like the way that it looks when the pi is still in there. But that's problem 1. Kind of recapping a little bit of what we did yesterday into homework. It brings back that idea of an inscribed angle being half of what a central angle is. The idea that they can have shared arcs here. So that arc QR is shared by that central angle and that inscribed angle. And then a little bit of right triangle trigonometry, which is always fun. And then radius and area of a circle, some older stuff. So a good problem to recap some things. We'll move on to 10-26 here. I believe in this lesson it goes to 10-29, but I think I cut out 10-29. So really we're going to be stopping at 10-28 today. But let's take a look at this one. So you've learned that a chord is a line segment that has its endpoints on a circle, like L and M here. What geometric tools do you have that can help you find the length of a chord? So this is going to be kind of bringing back to like what we were doing Tuesday, using that perpendicular bisector. But let's take a look at what the problem says. So examine the diagram of the chord LM in circle P. If the length of the radius is 6, and if the measure of LM is 150, find the length of LM. All right, so what that's saying is that this little arc out here, I'll try to draw it precisely, that red arc right there, measure of arc LM is 150 degrees. Sorry, writing on my stylus thing. 150 degrees is that arc length, and it's also saying that we know that the radius, so P to M, that would be a radius, and L to M would be a radius. We know that to be, those radiuses to be 6 units long. So we actually have a decent start here. We know that because my arc length out here is 150, that this central angle in here is going to be 150. And I'm going to try to put that in there somewhat small so it makes, so you can read it. That central angle in there is 150. But what else we know about these circles is that a perpendicular bisector will cut this chord and really bisect the chord and that angle. And so I'm going to try to put in a perpendicular bisector here. Let's see, is there a two-way line? I don't, well, I'll use this green one. Oh, I don't like that. We'll do a different one. Oh, sorry. What we have though is, so I'm going to put a perpendicular bisector this way and a perpendicular bisector going out this way. It's like that idea if we folded, if you look back to Tuesday's lesson, if we folded L onto M, we'd get that crease, that perpendicular bisector. And what that's doing is it's cutting that angle. It's doing quite a few things actually. It's making a right angle. It's making a right angle down here. Making a right angle down here. And it also cut our angle in half. And so we actually have a 75-degree angle in there. So if I redraw this triangle, what I really have now is a right triangle with the radius being 6, with this angle being 75 because it cut the 150 in half. And then this part down here is the part we don't know. It's the part of the chord, but it's only that x is only half of the chord. And so what we need to do is we need to solve for x and then multiply it by 2 so we can get the entire chord. There's a lot going on there, but really that idea, that perpendicular bisector, well, really where it starts is knowing that 150 degrees is that measure, and then that's the same as the central angle. And then you cut that central angle using that perpendicular bisector, which forms a 90-degree triangle. And we're able then to use, what we're going to be doing is trigonometry here to solve for that x. And so let's keep working here. We have the 90 degree down here, and so 6 is the hypotenuse, and x is opposite of it. And when you're talking about opposite and hypotenuse, that's a sine problem. And so what we're going to do is the sine of 75 equals the opposite over the hypotenuse, so x over 6. And then trigonometry from here, I'm going to put the sine of 75 over 1 and cross multiply. 1 times x equals x, and 6 times the sine of 75 I need my calculator for. So 6 times the regular sine of 75 equals 5.8 if I round it. And so what that is, and I'm going to try to clear some of this up now, that 5.8 is just half of your chord. All right, and maybe that helps you if you kind of compare that picture up here and down here. You can maybe see how that is related, that x is just half of that chord. And so what I'm going to do is I'm going to take my 5.8 and I'm going to multiply it by 2 to get the entire chord. And if I do that, 5.8 times 2 gives me an answer of 11.6, which is my answer for part A. That is a little confusing. We're going to be doing the same kind of process here for B. So if you wanted to, you can try to pause the video and repeat that process to see how well you understand it. And then unpause it if you get stuck, because I'm going to move on to part B now. And hopefully it helps kind of clear up this idea of using this perpendicular bisector and cutting the chord in half and cutting the angle in half. Same kind of problem here, just going to be a little bit backwards what we just did. So it says, what if we know the length of the chord? What if you know the length of a chord? How can you use it to reverse the process? So draw a diagram of a circle with radius 5 and chord AB that is 6 units. And so what I'm going to do here is I'm going to make a point, try to make it in the center of the circle. We know that AB has a length of 6, and we know that there is a radius length here. Oh, I don't want to use that. I would rather use a straight line here. We know it has a radius length of, and I'm going to draw the other one right away. We'll have the radius length of 5. Oh, wrong thing again. And what we want to know is, we want to find the measure of that arc AB, or we could find the measure of that central angle because we know that they're going to be the same thing. And so the first thing I'm going to do here is I'm going to use my perpendicular bisector to cut the chord in half and to form right triangles and to cut that central angle in half. So my first perpendicular bisector is going to go out here. And I'm really just eyeballing it because I don't have a tool for this. But we have that kind of that crease that forms if you folded A onto B. And what happens is that is no longer 6. It got cut in half, so this side is 3 and this side is 3. Now we also have a right triangle here. And we got our angle, our entire angle cut in half. And so what we're going to do is we're actually going to try to find this angle and then multiply it by 2 to find our whole angle. And that whole angle is going to be the same thing as that measure of AB. And so what we have here, I'm going to redraw my triangle for B down below. I have a right triangle. I don't know the angle measurement, so I'm going to draw like a little theta to say like I don't know that. Across from that angle is a 3. Like you can see right here, across from that angle is a 3. And then across from the 90 degree would be a 5 because that's a radius. And so I have a 3, and then across from my 90 would be a 5. And so I need to use inverse trigonometry this time to figure out what my theta is. But I'm running out of time in this video, and so I'll finish this problem in the second part and the other 2 problems in the second part as well.